Okay, this is the second hour of Physics 1A for March 29th. And we're going to pick up where we left off. So we just looked at the spring force right here. And to tie this back to what we were doing, we were wanting to calculate the work done by a variable force. So the spring force does in fact meet those kind of like criteria of being a variable force because the force is going to change with x the farther that you, for example, if an object starts from equilibrium, you stretch the spring and pull it to the right, then the spring is going to exert a force back to the left, and the farther you stretch it, the bigger the force gets. So this is a type of force that does in fact vary with position. In fact, what we could do is we could say that if we plotted the force as a function of x, and let's just say we do magnitude just to keep things simple, then it would look something like this. It'd be a straight line, right? Because it's just force. K is a constant, so. All right, so this meets the definition of a variable force, and really what we'd like to do is we basically like to take this idea, plug it in here, and calculate the work that's done by the spring force. So let's put those two ideas together. So we start off with the work done by a one-dimensional force, which is the integral of the force. I'm going to write it as fx dx. This means the x component of the force. We have to integrate between the initial position and the final position. Okay? So I suppose that it helps to draw a picture of that. So I guess what we could do is, let's take these two pictures here. Copy, paste. Bring this down here. Get rid of some of this stuff. So let's say that we move our object between two positions. So that was equilibrium. Let's say that this is the initial position here, okay? And let's say that we stretch it a little bit farther. So we're going to take our block and we'll stretch it just a little bit farther. So we're going to move it over to the right, like here. And then we'll just draw in some extra spring pieces here in black. Okay, so we're going to call this position here to be, we'll call this x initial. And we're going to call this position here to be x final. And between those 2 points, we want to calculate the work done by the spring. So now we know what x initial and x final are on our equation here. The spring force is going to grow, so I guess what I should do is I should draw on this picture that the force got bigger. And then indicate that that's still the spring force. Like that there. All right. And then I'll just write right here that the spring force is equal to negative kx. So all we need to do is just plug that into here. So we're going to get the work done by the spring is going to be equal to the integral of negative kx dx from x initial to x final. And what would we get? So the negative k is a constant. So what am I going to get when I integrate x dx? X squared over 2, and we don't really need a c because the plus c really only happens when you don't have limits, right? So we'll just write it's going to be negative k x squared divided by 2, and then we have to put our limits in. I don't know how you all do this in your calculus classes, but this is always what I did. I just drew a little line like this, x final, x initial, and that means we need to write this as basically negative 1/2 k x final squared. Here. Kind of skipping steps, I shouldn't do that. So we're going to get negative k over 2, we'll pull that on the front, multiplied by x final squared minus x initial squared, which I'm going to write like this. It's going to be negative of 1/2 obviously, you can write this however you want. But I'm writing it like this in anticipation of what we're going to be doing here in a few minutes. But that's the work done by the spring, basically. Okay. And we can pick some numbers. So let's say, for example, that x initial was 1 meter. And let's say that x final was 2 meters. And let's say that our spring constant k was equal to 10 newtons per meter. Then we could calculate what the work done by the spring here is if we use those numbers, right? Using those numbers, what we would get is the work done by the spring. Okay, I guess I should ask this question before I even do it. Do you think the work done by the spring is going to be positive or negative? Positive, negative? Okay, let's see what happens. So it's going to be the negative of 1/2 of k, which is 10. I'm just going to factor the 1/2 k out of all of this. Multiplied by x final squared minus x initial squared. So it'll be 2 meters squared minus 1 meter squared. So I think what we're going to get is 4 minus 1, which is 3, times 10, which is 30, divided by 2, which is 15. So we're going to get negative 15 joules. So it is negative. So if it moves from positive 1 to positive 2, the work is negative. Your question is, if it goes back to equilibrium, will the force be 0 total? At 0, the force is 0. Yes, Kelvin? Yeah. What about the work, though? What if we take... Here. What if we instead do, like... What if we let, with the same spring, we let x initial be equal to 1 meter, and we let x final be 0 meters, so that the object moves from here to here. This would be like, suppose the following question. I take a spring, it starts here, I stretch it out to this point, I let it go, the box slides back to the left and crosses through equilibrium at 0. You tell me, is the work done by the spring going to be positive, negative, or 0 if I do this? Positive? You sure? Let's see. All right, so x initial is 1, x final is 0. So we're going to be doing basically the same thing. We'll have negative of 1/2 of k multiplied by, we have to go, it's final minus initial, right? So it'll be 0 squared minus 1 meter squared. Sorry, that's a squared. That's going to be the work done by the spring. And yeah, it's going to be positive now, right? Because now we're going to have 1 times 10 times 1/2, but then there's a negative times a negative, so we end up getting positive 5 joules. Now let's see if this makes any sense, okay? Now, in the first position, we said that if we went from the drawn position, if I go from 1 to 2, then that would be my displacement, right? In this first part over here. Here, let's make it green. So we went from 1 to 2. This was our displacement, right? Would everyone agree? That that's the direction of our displacement in this first part that we did here in green? Okay. Is it reasonable that if the spring force is left and the displacement is right, that the work done is negative? Is that reasonable? Yeah, because the angle between them is 180 degrees, right? And again, it's all about the direction of the force relative to the displacement. When they're in the same direction, you get positive work. When they're in opposite directions, you get negative work. Okay. All right, what about this one? Does this one make sense? So this one implies that we're going from x initial of 1 to x final of 0. So that type of displacement would mean that we're starting from this position, but we're going back to 0, right? Nothing is to scale here, I apologize, but that would be delta x. So we got a positive value for the work here. Does that make sense? Well, sure, because the spring force is left. The work is also, the displacement is also to the left. So you get, cosine 0 is 1, so you get positive 5 joules. But you'll notice that the cosine doesn't really show up in these equations. And the negative sign really comes from, really, if you think about it, you'll get a negative sign when x final is bigger than x initial, and you'll get a positive sign when x initial is greater than x final, right? Let's look at another possibility. What if we went from this position over to a position over here where x final is negative 1 meters? What would the work done be then? So if we choose x initial is positive 1 and x final is negative 1, what would the work done by the spring be? That would be 0, right? That'd be 0, exactly. Because then it'd be 1 meter squared here and 1 meter squared here, and you just subtract them and you would get 0. Now, does that make sense? On the right-hand side, the spring is going to do positive work to get back to 0. But then when you get to here, the force is acting back this way, right? So basically, all of the work that's done by the spring to get it back to 0 kind of gets canceled out when we push back to here. So it ends up adding to 0. Okay, so we have this nice definition for the work done by the spring, but I don't know if it's so nice because you have this overall negative sign sitting out front. I put the negative sign out front because we do like to do final minus initial, right? It's not great, right? So what we'd like to do really is we'd like to come up with a better way to describe what's happening with the spring than this. And there is a better way to do it, and it's using what we call potential energy. Okay, so we'll come back to this definition here. The first thing we need to do, though, is to define what energy is. We want to set up what kinetic energy is, and then we'll define potential energy. Okay, so that's what the rest of the class is going to be about. It's about setting up those ideas. So the first thing to talk about is kinetic energy. And the first thing I'm going to say is, just as an aside to talking about kinetic energy, is the word energy in physics basically means, I don't really like this definition too much, but it works very well, is the ability to do work. Okay? That's what the physics definition of energy is. The ability to do work. So if something has energy, it has the ability to do work. So what are some examples of things that have energy? Well, batteries have energy. Would everybody agree with that statement? That batteries have energy? They store energy, right? Does everyone agree with that statement? Batteries store energy. You've got device. A spring can store energy too. Yeah, totally. But I'm just starting with something that's really basic, okay? Because I don't know that everybody really understands what a spring is. You know, I know that I just described them, but that doesn't mean you all understand what I'm talking about. This is just a picture. I didn't give you a spring to hold and stretch and under. You know what I mean? That's what I would do if we were in the classroom, but we can't do that right now. So let's talk about batteries, because everyone in this classroom probably at some point in time has bought a battery to put into a device, whether it be like, I don't know, like a remote control. You put a battery in the remote control when it dies, or it could be you're putting a battery in like a remote control car, a drill, whatever. Everyone uses batteries at some point in your life, right? So they store energy, and when we put them in devices, those devices can do work for us, right? Such as, for example, I can use my TV remote to turn on my television, and then pixels bounce around and create entertainment or whatever, right? So batteries are a thing that can store energy so that we can later use them to do work for us, right? Other types of energy that exist would be like the electrical energy that comes out of your wall socket, right? When you plug something into the wall, it does effectively the same thing as a battery does, just for a longer period of time, right? As long as there's no power outages, you can plug your computer into the wall socket and it'll keep working until there is some kind of a power outage, right? That's another form of energy. In physics 1A, we're not going to talk in detail about how those type of things work, but I want you to understand that all types of energy are effectively equivalent to each other. They all have this one thing in common, that they have the ability, anything that has energy has the ability to do work for us. You have energy as well. When you eat food, you put chemical energy into your body that you can then use later to go for a run or to do your homework or to do your job or whatever, right? All right, so energy is basically the ability to do work. It comes in all types of forms, such as, it's going to come in mechanical energy that we'll talk about in this class, electrical energy that I mentioned. It comes in the form of light that comes from the sun. The sun, bakes the planet with a lot of heat, a lot of light energy, which basically provides heat for the planet. Energy comes from all types of sources, okay? In this class in particular, we are going to talk about mechanical energy. And the first component of mechanical energy is kinetic energy. So, to understand what kinetic energy is, I'll just say to begin with that this is basically the energy of motion. Any moving object has energy. Any moving object has energy. So in order to describe what that energy is, we are going to take pretty much the same example we've been using up till now, but we're going to add velocity to it. So we'll take a box. Okay, it doesn't have to be. We don't have to keep using boxes, right? Let's just, okay, delete. Why can't I delete this? Is something stuck down? Delete, okay. All right, let's use a car instead. All right, so let's say I have a car. Let's say that's moving to the right with an initial velocity that I call v initial. And let's say that the person that's driving in the car hits the accelerator and increases the speed of the car so that the car moves faster. Oops. The car moves faster. And of course that takes some time, but eventually the car starts moving faster and it's moving with some final velocity that we call v final. So what we're saying is happening in this problem is that the driver hits the gas and the car accelerates. Now in this process, the engine is doing some work on the axles, which is doing some work on the wheels, which makes the wheels move, which then causes the car to move, okay? So I'm just going to say in general that there is some work that's being done by the car, and that according to our definition from above, that work done by the car should be equal to whatever the force that the car is exerting. Well, it's related to this basically, right? It's related to fx dx. So there's some type of a force being exerted here. And really, it's kind of a sum of multiple things that are happening. Okay, so what that force is, we're just going to call it f sub x. But it's not just going to be one force, really. Because when a car is driving, there's going to be a force that the car places to make itself go forwards. But there's also going to be forces such as friction, which act against it, as well as a drag force, which acts against it, as well as internal friction within the wheels that act against it. So let's just say that this force represents a sum of all the forces that act in the x direction on the car, okay? That's what that force represents, the sum of all forces acting in the x direction on the car, okay? Whatever they happen to be. It's the sum of all forces acting in the x direction on the car. And the work done by the car, then, should be related to the sum of all those forces, dx, as long as we integrate from its initial position, x initial, up to its final position, x final, right here, right? But we learned in the last chapter that because this car accelerates, and because it has some kind of a mass, let's say the mass of the car is m, there's a relationship between the sum of all forces and the acceleration the car experiences, which is the net force in the x direction is equal to mass times acceleration in the x direction. So, when we're finding the work done by the car, now I know that at the very top left there it says kinetic energy, and I'm still talking about work, but I promise you that we will get to kinetic energy. This is the whole point of what we're doing here, is to derive kind of where kinetic energy comes from. Okay, so just bear with me in case you're getting a little lost. So now what I want to do is I want to replace the net force in our work equation with max. I'm going to leave these limits off here for a second because we're actually going to change the limits of integration. Because the next thing that we can say is that we learned in chapter 2, I think, that the x acceleration of an object is related to the velocity of an object. How is it related? How is the acceleration of an object related to its velocity? It's not dv dx. The derivative of the velocity with respect to what? dt. Yep. The acceleration is the derivative of the velocity with respect to time. So we can put that in here. Let's assume that the mass of our car is constant, and that we can pull it out of our integral. So now what we end up getting is m times dv dt, and then we have an x right here, dx here. So now what we can do, I don't know, what do you think we could do next? Does anyone have any ideas? Now, just to be clear, the reason why we had to do something is because now we have acceleration here. We have x here. They don't really, doesn't really work very well. Any ideas of what I can do with this here? dx dt. What's dx dt? Yeah, that's velocity. So this would be the x component of the velocity, right? All right, well, if we do that, and the idea here basically is what we're doing is, let me put another step in here. We're really going to change it so that this dv stays like this, but we basically just take the dt and we kind of move it underneath the... Basically do that and just say, well, that's velocity. So we can write this as m integral of the x component of the velocity dv. And now, since we're doing a velocity integral, we can actually put our initial velocity and our final velocity into here. Okay. Oh, yeah, this is fine. This would technically be dvx right here, I should say. And this would be dvx here. So it's the same variable, dx and vx here. Okay, what's that integral equal to? To make it simpler, let's drop the x components and just say basically all we're really doing is the mass multiplied by the integral from v naught to v final of v dv. What would that be? Yep, so we're going to get mass multiplied by velocity squared divided by 2, and then we have to evaluate that from initial velocity to final velocity. Okay, let's go down just a little bit. So now what we end up getting is the work that's done, it's really the work done on the car, or by the car, however you want to put it, ends up being equal to 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. And then what we do is we kind of look at these two terms and say, it looks like the work done by the car is related to the final initial velocity squared multiplied by mass over 2. So what we're going to do is we're going to say, let's let, I think I have enough room left over here, right? So let's let kinetic energy, so I'm going to use the term K for kinetic energy, be defined as that term, 1/2 mv squared. So I'm just going to tell you over here that K stands for, capital K, stands for kinetic energy. I'm sure that in some of your other classes you use like KE. If you want to use that, that's fine. I don't like... In physics we really... In physics we love subscripts, but we hate variables that have 2 letters. Okay, so you're not going to see many variables in physics that look like this. You're almost always going to see variables in physics that look like just a single letter. Because to me this looks like K times E, you know? But if you want to write your kinetic energy like that, that's fine. Just know that when I write capital K, that's what I mean, is kinetic energy. And it's defined as 1/2 mass times velocity squared. I don't think that's probably a surprise to anyone here. If you've taken physics before, you probably memorized this. The kinetic energy is 1/2 mv squared. And then we get this nice relationship here, which is that the work done, and this can be generalized to more than just the system we're talking about here, the work done tends to be equal to basically what we call the final kinetic energy of our car minus the initial kinetic energy of our car. And then this formula gets written normally like this. Work is equal to the change, because it's final minus initial, of kinetic energy. We call this the work energy theorem. The work kinetic energy theorem, whatever you want to call it. And what it says is that the work done on an object is equal to the change in kinetic energy of the object. That is to say that when you apply work to a system, you're going to increase the kinetic energy of the system. If you apply negative work to a system, you're going to decrease the kinetic energy of the system, such as when a block is sliding along a surface and it comes to rest. You push a block, friction slows it down, right? But there we go. This is going to be one of the most useful relationships that we're going to have in this class. We are going to learn a better version of it that I'm just going to call the conservation of energy. But this is, yeah, the work energy theorem. Does anyone have any questions? So kinetic energy is the energy of motion. You have to have a velocity to have kinetic energy. So I derived this in one dimension, Andrew, but this is perfectly general. Because kinetic energy is a scalar and work is a scalar, it turns out that this is also going to apply to systems in which it is not moving in a straight line. So let me give you an example that I think is relatively simple. Let's say I have a cord and I have a mass at the end of it, and this cord is suspended from the ceiling up here at the top, but it's free to pivot, and in its motion, let's assume that there's really very little work done by friction up here at the pivot, so it's a very close to frictionless pivot. And let's say that it starts off at some elevation right here, and it swings down to here. Oh boy, this is not a simple example, I just realized. Anyway. So in this case, even though the pendulum is going to travel along a curved path, this equation still applies. If you can calculate the work that's done by gravity, which isn't exactly easy, because gravity acts down, and the path that you're traveling along like this means you need to do an integral, technically. You would need to do... where is it? You need to do this. But it would still work. It would work. We'll probably look at something like this next time, if we have enough time left over. Where we actually calculate the work done by gravity when you go along a curved path like this. But, yeah, this isn't just for 1D. This is true for any dimensions. Which is part of why it's really powerful. Because we're going to use this to solve some really complex problems that Newton's second law wouldn't allow us to solve. In fact, what you can understand from this is that this is an alternate version of a way to solve problems. It's an alternate from Newton's second law. So up till now, we've used Newton's second law to solve problems. Now we have kind of another thing we can use to solve problems. And this one's going to be really useful when we have forces that are not constant. And when we have accelerations that are not constant. That's what this is going to be really useful for helping us to solve. Here? Yeah, something like that, Andrew, yeah. Really all you need is the angle between the path and the weight, but again, we'll try to do one of these if there's a little extra time. There's an example in your book of a person that's pushing a child on a swing. That's the one we'll do. I often find it's like not that helpful, but if we have extra time, I'll do it. Because I'm sure some people would like to see it. Okay, so work energy theorem. We'll put that in our back pocket. We need to Wait a minute. When you said wx and wy, do you mean like the work in the x direction and the work in the y direction? Oh, I guess maybe you're thinking of like these terms here, fx dx and fy dy. Just understand that work doesn't actually have an x or y component because it's a scalar. So if what you meant is like these kind of things, then maybe. But the reality is that for this type of a problem, we'd rewrite our equation using angles as opposed to x and y. But we'll come back to that. I don't want to get off track. Changing kinetic energy in the x? No, you wouldn't do that. No. Kinetic energy doesn't have x and y components. I mean, like, let's say that I have an object that's moving in space, and let's say that it has a velocity v, but that velocity has a component that we call v sub x, and that velocity has a component that we call v sub y. Then I can write the kinetic energy, if I want to, as 1/2 m times vx squared plus vy squared. But this is kind of meaningless because vx squared plus vy squared is the same thing as v squared according to the Pythagorean theorem, right? So while you may see people write things like this, and it may be useful, this may be a useful thing to do from time to time, I don't know. Well, I mean, I can think of problems that I did like this a long time ago, but like in reality, this is good enough for this class. Absolutely good enough for this class. You will almost never have to do anything like this. All right, so the next thing to do, we've got one type of energy, okay? I said there's all kinds of different types of energy. In this class, we're going to be talking about mechanical energy, and this is one component of mechanical energy. The other component is what we call potential energy. So potential energy is a type of stored energy, okay? Potential energy can exist in the way that it's stored inside of a spring. It could exist in a bow and arrow, such as if you take a bow, right? And you take an arrow and you stretch the bow out. So you put an arrow, you notch the arrow inside of the bow here. Then you store energy inside of the bowstring that can be released when you let go of it. So potential energy is a type of stored energy. The most common form of potential energy we're going to see in this class is going to come from gravity. Because if you think about it, you can store energy in the gravitational field of the planet, just like let's take my old cell phone right here. If I take this and I lift it upwards, we're going to say that it gains potential energy. And when you lower it down, we're going to say that it loses potential energy. And why is that? Well, it's because if I were to let this object go, we know that it's going to gain speed. And the higher that you lift it, the more speed that it's going to gain. So more stored energy or more potential energy. Okay? So let's specifically talk about gravity first. Now, in order to describe the potential energy due to gravity, all we really need to do is just to have a system where we move an object between two positions. We'll calculate the work done, just like we did in the last problem, and we'll compare that to, then we'll come up with an expression for the potential energy. So, to do this, we start off with just an object, like let's just use a ball. We're going to take this ball, and we're going to move it upwards. So, come on. Let me select the ball. Copy, paste. So we're going to move this ball straight up. And it is going to start from an elevation that we're going to call y1. I guess I'll just use vectors for all this stuff because I think it makes it look better. So we're going to start off right here from an elevation. We're going to define the ground to be y equal to 0. So this is going to be, we'll call this position right here y initial. This is y equal to 0. And we're going to lift our object up to a higher height. So it's going to be lifted up to a position that we're going to call y final. And I guess I'm measuring these distances relative to the center of the ball. Doesn't matter what point you pick, you just need to be consistent. So this is going to be y final. Okay, and we're going to say that this is Earth. which means there's a gravitational field that acts downwards, and that means that on this ball, we can draw the force of gravity. The force of gravity acting on this ball goes down. I kind of want to make that a different color as well, so it's not the same as the thing. So that's the force of gravity. The force of gravity is constant in this case. Yeah, we'll just say that's mg. And let's just say that we throw the ball from here up to here, okay? That's what we do. The ball is thrown from this location up to this location. This doesn't have to be the max height. This doesn't even need to be the starting point. This is just a ball in motion. We'll just say a ball is thrown in a straight line, so just straight up. And what we're going to do is we basically want to calculate what is the work done by gravity. That's all we're going to do. All right, so it's thrown up. It starts here. It moves to here. It's going to have a displacement vector that would point upwards. So the displacement would go this way. It's dark blue or something. This would be our displacement vector, delta y. Now, according to what we've learned before, for the work done by a constant force, in this case gravity, all we need to do is to take the size of the force of gravity, and dot product it with delta y, right? So, in this case, that's going to be, force of gravity is just mg. Delta y is y final minus y initial. And then we need to multiply by the cosine of the angle between the two of them. What would that angle be in this case? It's not 0. What's the angle between the weight vector that goes down and delta y that goes up? Yep, 180 degrees. So we end up getting the negative of mg times y final minus y initial. I'll just say that's the work done by gravity with the little g here. Now, I'm going to put to the right of this just what we got before for the spring, because I want you to see just how similar these results are. For the spring, what we got was the negative of 1/2 k multiplied by Do you notice they're really similar to each other? What do they have in common? What are the things, when you look at these two equations, what do they have in common? No, they're not. The spring force is not constant. The gravity force is constant. The spring force was not constant. That's not one of the things they have in constant. Okay, initial and final show up. It goes final minus initial, right? Final minus initial, exactly. Those are both there. What else is similar? Yeah. They both have this negative sign. That's kind of weird, right? Why is that negative sign showing up there? Okay, so what we want to do is, because both of these have this negative sign show up, and because they both have this final minus initial, it really kind of makes you think, huh, I wonder if this would change in some way, right? If instead of having my object move along a constant path like this, what if I made it move at an angle? right? So what if instead of making it do what I just did, what if instead I took my ball and I moved it along an angle, okay? And instead of throwing it, maybe what I do is I basically just take a line and I draw it from here to here. Make it some kind of different color, this blue. What if that was my displacement? We'll call it delta R or something like that. Would my answer have been any different? So I take a ball, and now what I'll do is I'll basically I'm just going to take my object, and instead of moving it like straight upwards, we're just going to physically, with our hands, we're just going to move it along in a straight kind of like line motion like that. Does that make sense? So what about along this path? What would the work done be? Well, we would need to know an angle, right, in order to make this work. So let's draw an angle in here. We're going to make this angle right here theta. So now what would the work done by the force of gravity be in this case, along this path? I don't know if I have enough room here to do this, but we're just going to try. The work done by the force of gravity should once again be equal to force of gravity dot product with delta R now. Here, let's just move down here so there's more room. I don't want to squeeze everything inside this little space here. Even if I did and it fit, it would look pretty... It would be hard to read. Okay, so now we've traveled along this path that I've defined as delta R. So the work done by gravity now is going to be equal to force of gravity, which is mg, multiplied by the magnitude of delta R. And then I have to multiply by the cosine of the angle between the weight and delta R, which delta R goes this way. What's the angle between the two of them? The angle between delta R and the weight vector. What's the angle between the two of them? It's not minus. Is the cosine of 90 plus theta in any way related to the sine of theta? Y plus. This angle is 90 degrees. This vector points down, so 90 plus theta. That's why it's positive. Does that make sense? Delta R is a vector that goes this way. Mg goes down. So cosine of 90 minus theta is equal to sine of theta, right? But cosine of 90 plus theta, how is that related to sine? Anyone know? I think I know what it is. I'll see if you all know the answer. No, it's not sine of 90 minus theta. I think it's just negative sine theta. Someone want to go look it up? I'm pretty sure that this is equal to the negative sine of theta. Does anyone want to go look that up for me real quick? I mean, I could prove it. We're just running out of time. I want to take a break in 5 minutes. I'd like to finish this. Otherwise, I would just prove it for you. So, while you all are trying to look at its positive sine theta, sine of 90 minus theta is, look, so I know that this is true. Cosine of 90 minus theta is definitely equal to sine theta. And I'm pretty sure cosine of 90 plus theta is equal to, is negative sine theta. Okay, yeah, you're all agreeing. That's good. Okay, now if we go back and look at our picture, because the idea was we want to move the ball to the same elevation, what is delta r times sine theta equal to? Don't worry about the negative sign, because we actually want the negative sign to end up at the end. What is delta r times sine theta equal to in our picture? What? Change of y. That's right. So delta r sine theta is equal to delta y. Because delta r goes this way, theta is here. You can imagine that I could drop a line right here, and the height would be delta y. So delta r sine theta is equal to delta y. That means that the work done by gravity along this diagonal path is exactly the same. This answer and this answer are identical to each other. So taken together, what all of this means is that the work done by gravity is independent of the path taken. It doesn't matter what path you take it along. All that matters is the endpoints. Does that make sense? When you look at this equation right here, it's just the endpoints. And in fact, it's really just the elevation that we care about. How far above the ground are you? So as a result, because the work done by gravity is independent of the path, it makes sense to just say that, well, this thing, mgy, must be representative of something right here, right? It must be representative of something that we can use to be calculating work done by gravity. So what we're going to do is we're going to basically say, let U represent the potential energy due to gravity, so U sub G. So, okay, so big U is potential energy. And we're going to let the potential energy due to gravity be defined as mgy. Okay, then the work done by gravity then is going to be equal to the negative of because you have mgy final and mgy initial here. And then we can basically say in general that the work done by gravity is equal to the negative of the change in this quantity that we're calling potential energy. And we can do the exact same thing for the spring. The spring up here, it has the same feature. It doesn't matter the path you take to get between these points. So for the spring, we just say to let the spring energy, U sub S, be equal to 1/2 k times x squared, because you have 1/2 kx squared minus 1/2 kx squared, final minus initial. And then what you get is basically that the work done by the spring is the negative of the change in potential energy stored in the spring. So what we can do then is we can basically say that each of these things represent this quantity represents the amount of energy stored in the spring. And this quantity up here, mg times y, weight times elevation, represents the energy stored in the gravitational field. And those are the two forms of potential energy that you're going to see show up in this class. Pretty much the only forms of potential energy that are going to show up in Physics 1A. You will find other types of potential energy, but they all have this same feature, that the work done by the force is independent of the path taken. And there's always a negative sign that shows up between the change of potential energy and the work done by a force. This relationship in general makes both of these forces what we call conservative forces. And conservative basically means what I said right there. Conservative force is a force... I can't write it like that. I have to say a conservative force is something where the work done by the force is path independent. And if that's confusing to you, we'll talk about what a non-conservative force is next. And I'll give you an example. Friction is an example of a non-conservative force. But we need to take another break. So we're going to take a break till 4:13. And if you have any questions, let me know.